I would like to welcome everyone to our initial joint NISS and KINNIS web series on collaborative data science. As I said, this is kind of the first one that we're doing, so really appreciate our two speakers today for being the guinea pigs in trying this out. We do have some more lined up. We're hoping to do these once a month, so definitely check out the NISS website for all of the upcoming seminars. So for each one of these seminars, we are celebrating interdisciplinary collaboration. So each of the seminars will have two speakers, a data scientist and a subject matter expert from another domain, who have successfully partnered together to solve a problem. So that is what this seminar series is all about. And I would like to give a shout out to David Madison at Cornell, who is kind of the spearheading of all of this. And this was his idea and his brainchild. He unfortunately can't be here right now, but this is all thanks to him. And I also will give a shout out to, we have a whole organizing committee that has done a really great job of coming up with speakers for the series. All right. So that's the series. Let's talk about what we're going to talk about today. I'm very thankful for Claudie Beaulieu and Rebecca Killick, from probably the greatest time change difference of two collaborators. Claudie is from the University of California in Santa Cruz, and Rebecca is from Lancaster University. And today they're going to talk about changing climate, changing data. And so you came here to listen to them talk, so I'll stop talking and turn it over to them.
All right. Thank you, Emily, and thanks to the organizers for putting together this event. And I think I can speak for both Rebecca and I that we're super excited to do this team talk for the first time and to be the guinea pig here for this new series of talks. And today we're going to share our journey through our collaborative research between climate science and statistics. Since this is a team talk, we thought we should, share who is the team to start with. And I'll start with me. So I did an undergraduate degree in statistics and then a PhD in water sciences. And my main goal was to use statistics to address climate and environmental change related questions. And so I guess I'm kind of halfway in between a domain, scientist, climate scientist, and a statistician. And Rebecca is a statistician, did a PhD in statistics, and their main interest is to develop statistical models and methods for non-stationary time series analysis and change points, and has done work in a wide range of different applications, including the environment, right? And so I very much hope it stays on top of the priority list so we can keep doing cool work together. So I highlighted here the keywords in our research interest to show that there's quite a bit of synergy and common interest here. Rebecca and I met at the Isaac Newton Institute for Mathematical Sciences in Cambridge in the UK about 11 years ago. And at that time, we were both like more, junior career stage in our career. So if you haven't heard about the Isaac Newton Institute, it's a visitor-based research institute in the UK, in Cambridge, where people come together to address a certain, research topic within the mathematical sciences, broadly, and has like the and they provide the support and facility to kind of make this all happen. And in 2014, there was a program that ran about Change Point that brought together statisticians as well as domain scientists. And we both went to that program, and that's where we met via Idris Ekley, who's a professor at Lancaster, who knew both of us and sort of had the vision that we collaborate well together, and organized a meeting for us to like brainstorm about, you know, potential collaboration and so on. And that's kind of how like it all started, right? It just needed a moment to sit together and brainstorm, really. And so we discussed problem related to climate change that we could collaborate on, and specifically what needs to be done in terms of methodological development for change point detection methods to help solve these problems, right? And one such, you know, question or problem back then was related to the rate of global warming. So here I have a figure showing global mean surface temperature anomalies relative to the period of 1951 till 1980. From 1850 to 2014, which is, you know, when we had that first meeting. So this is what the record of global mean surface temperature looked like then. And at that time, you know, there was a lot of debate in the literature as to whether or not there's been a slowdown in warming. And just to guide your eye here, I've drawn, you know, some lines before and after the hypothesized slowdown in warming. And so you can see that it kind of looks like, you know, the rate of warming all the way from 1970 till the late 1990s, early 2000 was pretty steep, and then there's a slowdown after that, okay? So this was heavily mediatized, you know, lots of discussion in the literature and so on. So of course, if I pick, you know, cherry pick a time in a time series like this, like, you know, 2000, and fit the trend before and after that, chances are that I will conclude the trends are different, right? But I'm not really accounting for an objective search of all potential, you know, changes. So that's one thing, right, where change point detection methods can help. And then the other thing is there's quite a lot of short-term memory in climate data, and that needs to be taken into account, right? Because autocorrelation, which is what I call short-term memory, autocorrelation can either mask or exacerbate a warming trend, especially over a short period of time if it's not taken into account. So in the first part of the talk, Rebecca will discuss methodological developments that went behind, you know, eventually addressing this question of as to whether or not there was a slowdown in warming. This is what the global mean surface temperature record looks like now, okay? Now we have all the way until 2024. I don't want to sell the punch, but you can see that the appearance of a slowdown is gone. And the last 10 years or so on the record were the warmest. And so now there's a new debate, discussion in the climate literature, which is also heavily mediatized as to whether or not global warming has accelerated, okay? And so once again, we can look at that question using change point detection methods. And this is what I'm going to be focusing on in the second part of the talk. So that's it for my introduction. And now I'm going to hand it over to Rebecca for the first part of the presentation.
Thanks, Claudie. So I'm going to talk to you a bit about how we actually do this from a statistical perspective. Next slide, Claudie. So Claudie's mentioned a little bit about change points, but we should probably introduce what we mean statistically by change point detection. And so there's lots of different potential things that can be determined by a change point. Traditionally, we just say that we have collected some data. The data is time ordered. That just means, one data point comes after another. And we say that a change point is at a location tau where the statistical properties of the data prior to that time tau are different from the data after time tau. So that's what we kind of mean statistically by a change point. And there's three examples here on the side. On the left is a change in mean, where the mean is constant for a period of time, but then at some time point it switches to another mean, and then it can switch again for multiple change points. The middle one is a change in trend, which is what Claudie was talking about on the last slide, and the one on the right is a change in variance. So these are just three different examples. You can have a change in absolutely anything, a full distributional change, a quantile change, rank change, whatever you can envisage. It's just important that the statistical properties prior to tau and after tau, the change point location, are different in some way. Okay, next slide. So one of the easiest ways to think about change point detection is what Claudie was saying originally, where you're doing some kind of model fit before and after the change, and you want to compare that model fit with the change point in place versus the model fit over the whole data without a change point. And so we know one of the ways to do that would be a likelihood ratio test. And so a likelihood ratio test statistic here, based on the log likelihoods, would be, to take the sum of the two segments of data. Let me just do my annotation. So this is the likelihood for the model prior to the change, the likelihood for the model after the change. You add those two together, that gives you the likelihood for the whole data set, including a change point at tau. And then this last part here is comparing that to the model without a change point, so where we're just fitting a single model, no change, to the whole data. The challenge here is that, obviously, as Claudie said, we don't know where this change point is, and we need to take account of that because if we don't take account of the fact that we get to choose where the change point is, we're missing some of that variability. So we take the maximum here over all potential change point locations. This is key because you can't just optimize this via a maximum likelihood because the tau is a discrete parameter. And so we need to look at this maximization over all potential change point locations. And just like in any other likelihood ratio test, we then say if this likelihood ratio is larger than some threshold, then we say that we prefer the change point model to the no change point model. If we prefer the change point model, then whichever tau gives us this maximum likelihood ratio test statistic, that is the value that we're going to use as the estimate of our change point location. Okay, next slide. So that's for a single change point. What about multiple change points? So if instead we say that we have multiple change points now, so we've got tau 0 up to tau n plus 1, we typically say that tau 0 is 0, and then n plus 1 is the end of the data. So that means we've got m change points in total within our data set. So if we think about that likelihood ratio test again, what we can do is we can say that that is a minimization over the 0 change point or 1 change point model, so m being 0 or 1, of this test statistic here. So we've got minus the log likelihood here, And then we've got this penalty here, beta m, where obviously if m is 0, then you just have the likelihood of the whole data. And if m is 1, then you just have a single beta term coming in. And the minimization of that is going to precisely do exactly what I had on the last slide to say which model is preferred, the model with no change points or the model with one change point, using that threshold beta to choose between the two. And so you can get that threshold beta in the single change point case through different asymptotics. There's two common ways to do it. One goes to a extreme value distribution, and one goes to a function of Brownian bridges. And so we can then think about extending that from just the 0 change point versus 1 change point to any number of change points at the bottom here. And so all I've done is I've removed that restriction of the 0, 1, and that allows us to compute that for any number of change points. Okay, next slide, Claudie. So the challenge there is well, how do we actually do that? So in essence, we're taking the models for each of the individual segments here. We're adding those up. So we've got an assumption of independence here between the different segments, the data between the change points. And the challenge here from a statistical perspective, well, there's number one, how do we characterize the model in each individual segment? But also, how do we actually decide what are the how many changes we have within our data and where they are? And this is really the crux of change point estimation. It builds all on the model building that we have in any statistical domain, and you can use any model within each of these individual segments. And then the key for takes change point detection further is about how you decide how many changes there are and where they are. So in any generic data set, that gives you 2 to the n-1 possible solutions. And so that's really, really challenging to be able to actually fit these models and decide how many change points there are and where they are. It's more from a computational perspective. Next slide, please, Claudie. So some earlier work of mine with Idris Eckley and Paul Fernhead back in 2012, we came up with an algorithm that allows us to solve this computational problem exactly. And so what it does is, first of all, we have a dynamic programming step that allows us to, instead of looking at the whole space, we basically move from the beginning of the data through to the end of the data. And as we do so, we just worry about where the last change point location is. And that allows us to, at any point, go back to where the last change point was, and then essentially bunny hop back in time to say, well, the last change point, let's say, is at 100. I then go to time when I was back at time point 100, where was the last change prior to that? And that allows you just to bunny hop, and that reduces from 2 to the n-1 calculations down to order n squared. The beauty in the Pelt algorithm is that we can get even faster by using a pruning technique. And this basically says that if we're at some point during the algorithm, this capital time T here, let's say 150 in this example, as we look back in time and we say, okay, well, where is the last change point? The dynamic programming says you have to consider every single location as a potential last change point location. What the pruning does is it says this little time T here is unlikely to be a last change point location. And the reason for that is we've had this huge change here just prior to S. And so realistically, looking back in time, any time point prior to this big change point isn't going to be the last change point prior to capital T. And so we've got some mathematics that gives you the pruning rule, the condition that needs to be satisfied for that to be the case. And that allows us still to have an exact optimization of the problem. So little s here, this is a potential last change point location, but little t isn't. We can also remove this from any capital T going forward as we advance in time. And so that reduces from an order n squared algorithm to an order n algorithm. And so that allows us to actually be able to fit a lot of these models in practice. Okay, next slide, Claudie. So that gives us the tools to be able to actually fit these models, but that doesn't mean that climate scientists are going to be able to use them appropriately. So tools are simply not enough. They need the ability to be able to actually use these tools in practice. So we've got some example here of different ways that you can make mistakes. This first one in A here is where you should be fitting a change in mean structure, but somebody instead has fit a trend structure. B is where you should be fitting a trend, but climate scientists occasionally use more sophisticated tools like these changes in mean, and then you get this stepped change approach here, but those change points are meaningless. They're not really there in the data. As Claudie mentioned, autocorrelation is very, very important. C here is an example where there isn't any change points within the data, and you've got a trend line that comes through, but really it should be a flat mean if you take into account the autocorrelation. And then D is where, again, with the autocorrelation, if you fit a change point model, you will find change points where they just don't exist, and it's just due to autocorrelation. And so the key is when you potentially have hundreds or thousands of time series, you can't necessarily look at each one of these individually to be able to ascertain, well, this one should be a trend, this one should be a changes in mean, this one should have autocorrelation, this one shouldn't. And so this is kind of one of the problems that Claudie and I were looking at in one of our earlier papers when we were looking at this, has there been a hiatus, has there been a slowdown in the rate of warming? Next slide, Claudie. So what we did was we created an R package called MCPT. This allows you to fit a whole suite of different models to the data automatically, including trends or just means, autocorrelation or no autocorrelation, and allows you to fit with change points and without change points. And so this is really the suite of models that are most commonly used within this environmental climate problems. And so this allows people to be able to fit all of those automatically and choose which is the best one according to some information criteria, such as the Akiki information criteria. So this is available on CRAN and has been used in several different papers in the climate literature. Next slide. So this is the sort of thing that you can get out as a summary plot. These are the different models that were fit back in 2014 when we were talking about had there been a hiatus or a slowdown in the rate of warming. It's clear that you can kind of see the change points in the different models, some with trend. We included the autocorrelation in the trend fit here just so that you can more visually see the difference between the autocorrelated and the independent data sets. The key thing is the top one, the trend change point plus AR1 model was chosen as the best model if you use AIC here, and that has no change point detected beyond the 1970s. And you can clearly see here there's been a change in autocorrelation at that time point as well as a change in trend. Next slide. Sorry, over to you again, Claudie, to continue.
Yeah. Thank you. Yeah, so I'll take it over now to discuss a more recent paper that we collaborated on. And so we did this analysis looking at whether or not there was a hiatus, and like in the end showed there was no hiatus. And then more recently, discussion in the media was around whether or not there's been an acceleration in warming. And so when I saw that, I reached out to Rebecca and other collaborators, Robert Lund, Colin Gallagher, Xueng Shi, that we all, had been working together on other papers. And ask them, if they wanted to look at this question together and assess whether or not there's been an acceleration in the rate of warming. And so I'll be discussing that paper now. Okay. Okay. So when we worked on that paper was mostly, in 2024. And so here we have the global mean surface temperature records that were available at that point. Earlier in the talk, I shared the Berkeley record, but we also used the record from NOAA, Hadley Center, and NASA as well. So they're all presented here until 2023. And we analyzed these time series of global mean surface temperature with change point methods to see if we can detect a more recent acceleration. We used two types of change point models to do that. So this is the first type we use here, presented as an example. It's a discontinuous model in that we don't force the two lines to meet here at the change point. Okay. And so we use this model to represent global mean surface temperature as a regression function plus some errors. And we have here the general form for that regression function that fits. It's a piecewise linear model where we have different linear regressions in the different regimes. The regimes are separated by the change points tau. There are an unknown number of change points m, giving m+1 different regimes. Okay, and then in addition to discontinuous models, we also included here in our analysis models that have a continuity constraint where we force the two lines to meet at the change point, right? So we have that constraint here. In the climate literature, it's been argued that this kind of model is more physically plausible for representing surface temperatures. And so that's why we included that as well in our analysis. And so overall, we fit a series of different change point models to accommodate different assumptions one might make about global mean surface temperature data. I've just shown you two different types of regression function that we used, and then we make different assumptions about the errors as well. First, we use first order autocorrelation to represent them, which is kind of a commonly used model in climate literature, like a go-to model in detection studies, such as in the IPCC, the Intergovernmental Panel on Climate Change. And we're going to let that first order autocorrelation to either vary at the change points with the other parameters or force it to remain fixed through the whole time series. And then we decided to use a higher order autocorrelation as well based on our own inspection of the residuals to see what happens. And then this is a little bit cheeky, but we included also a model where we assume the errors to be independent, even though it's wrong, just to see what happens when we do that. Okay, and so we have these different configurations, right, with different set of assumptions. And the goal is not to find the one best model, but rather to assess if any of those yield an acceleration in warming after the 1970s. And so this is one set of results. I'm not going to show you everything, but this one is results we got with a continuous model on the left, this continuous model on the right. This assumes first order autocorrelation. And you can see that in both cases, we pick up the change in the 1970s that we know about, that is like, has been discussed a lot in the literature, but nothing beyond that, right? Like no recent acceleration in warming in either case. And this is also true with other autocorrelation models in the background, although the timing of the changes might vary a little bit, but there's no change beyond the 1970s. The one model that yields an acceleration is a model that is discontinuous and that assumes independent errors. So you can see that in this case, we do detect, an acceleration a little bit after 2010. We also detect kind of a slowdown, right, in the late 1990s. But the problem here is that we don't account for autocorrelation when we know that it's present in the time series, so it's not valid. Yeah. Okay. So earlier this year, when the data points were made available for 2024, we updated our analysis and showed that the results are the same. We still don't detect an acceleration in warming with the 2024 data point. At the same time as we were writing this paper, James Hansen and co-author published a study where they made a prediction of an acceleration in warming. And so this is a figure from their paper here showing in green sort of the rate of warming over the period 1970 till 2010 and then continued, and their accelerated warming prediction here that is due to reduction in cooling aerosols. So we don't detect that in our study, right? We couldn't detect an acceleration after 2010. And so maybe it's not there, or maybe it is there, but it's just too small or too recent to be detectable, right? And so another question we addressed in this paper is, when could we detect an acceleration, assuming it's there? And so this is what this figure is showing. So we estimated the minimum magnitude required for an acceleration or slowdown to be detectable given different time for that a change or acceleration, and different vantage point as we extend the record further in time. And so the color here is the minimum magnitude required for an acceleration to be detectable. So you can see that if we extend through time, it becomes easier and easier to detect a change, right? So the minimum magnitude required becomes smaller and smaller. And if we go towards the end of the time series, then it becomes harder to detect a change because there's very few data points after the fact to estimate it. And we didn't focus only on 2010 here, but rather like a range of possible times, because other studies have discussed acceleration at different times, right? Not just 2010, all the way from 1990 to 2015. So we wanted to encompass all of these possibilities here in our estimate. And so if we just look at 2010, for example, our conclusion is that a change at that time is just either too recent or too small to be detectable. And just as an example, an increase of about 50% in the rate of warming at that time would be detectable in the early 2030s, right? So we're just not quite there yet in terms of detection if there is an acceleration in warming. So just repeating our results, right? Like an acceleration is not quite detectable yet based on our analysis. And I think it's important to be very careful with interpreting changes in trend in like short spans of time like this, to not, come to conclusions too quick for a change in either a slowdown or an acceleration in warming. I just want to stretch that these results don't challenge the fact that human activities are causing long-term global warming, nor that we had record-breaking temperatures the last 2 years. Just that we can't quite detect an acceleration yet based on surface temperatures. I think it's important to stretch that because there's been a lot of false information circulating on social media after our paper was published. So this is a figure that was sent to me by a fact checker at Facebook that has a screenshot of our paper that you can see here. And then it says global warming is a hoax, right? And that's not aligned at all with what our paper is saying, with the message of our paper. And so I think it's important to stretch that our results don't challenge that fact. It was kind of nice to have the opportunity to correct the information circulating and set the record straight on social media. All right. So I'm going to hand it over to Rebecca now to share some thoughts on collaborating together and more generally.
Yeah, so we were asked to kind of comment on collaboration and what we think works and why we've managed to have successful collaboration together. So one is, Claudie and I have worked together a long period of time through several children on both sides, and I think a lot of the reasons why we can work together is because we have mutual respect for each other. So Claudie very much understands what motivates me and what is good research in my field, and I equally understand from Claudie's perspective, what is good for her and what's going to help her in her career. And so it's this mutual respect that has allowed us to come together to work on things that are both important from Claudie's perspective in the ocean sciences, and then also important from my research perspective in statistics. So developing new models and new methods to be able to solve some of these problems that Claudie wants to be able to address. And I think that's something that has really come from our relationship. It's not that it's a service relationship. It's not statistics providing a service to ocean sciences. It's that mutual benefit and mutual respect between the two of us. And I think a lot of this kind of comes also from our own personal respect for each other as well. When we were kind of discussing about our collaboration, Claudie and I were going down memory lane and thinking about lots of nice times that we've had together, both in the UK and in the US. And one of the beauties of our time zone difference, so Claudie's on the West Coast in the US, I'm in the UK. We have 8 hours time difference, usually 7 at the moment because of daylight savings, but usually it's 8 hours time difference. And so often, that can be challenging when you're trying to find times to meet when it is kind of working time for both of you, because there is no overlap in working hours. But it also provides some benefits as well. So we've had several times where we've managed to accelerate a paper because I've been able to work on it. And then, we've had a meeting at the end of my day, which is the start of Claudie's day. Claudie's been able to progress things forward on that side. And as Claudie reminded me that I'd forgotten, we did have one overnighter where we basically stayed up a very long time to work together. And Claudia was saying, "Oh yeah, shouldn't you be taking your kids to school now?" So yeah, so there's that kind of mutual understanding and willingness to work on things together to progress things quickly. And I think that's really the crux of why Claudia and I have worked well, is that willingness to open. So I'm willing to learn about ocean sciences. Claudia's obviously willing to learn more about the intricacies of the statistical aspects on my side as well. And I think that's really what comes forward, that and the fact that it is that mutual appreciation that there needs to be benefit on both sides from a research perspective. So I'm aware of the time, so I will let you sum up now, Claudie.
Yeah, okay. Yeah, thank you for that. And I just want to share some thoughts as well. And I mean, first, I want to reinforce everything Rebecca just said, and highlight that, like, above all, it's just been really fun to collaborate together, right? I think we just have a lot of fun doing this work, and maybe reflect a little bit more generally on collaborations between statisticians and climate scientists. And on that, I just want to mention that, like, there's actually a large statistical component to climatology, and a need for collaboration with statisticians that is recognized and understood. And there are conferences that are dedicated to bring these two groups of people together. Like last summer, we were at the International Meeting on Statistical Climatology, for example, right? Like and that's the type of meeting that is meant to bring the two communities together to collaborate and think about problems together. There's definitely still barriers, I think, to collaborating across, the two communities. And just giving my 2 cents here as to how, this could improve. And I think that on one hand, I think it's important for statisticians to think about accessibility, right, to climate scientists. So climate scientists think about mechanisms and search for the physical meaning and so on, right? So I think it's important to try to explain statistical models, for example, in terms of these mechanisms. And I'm not saying this because I'm as guilty as anyone. I know better, but it's definitely something that I think is important and that I've seen as a barrier. And then on the other hand, I think for climate scientists, I think it's really important to acknowledge statisticians' contributions. Bring on a statistician early on when you write the proposal and give them a formal role on the proposal, right? Or write the paper together as co-authors, right? As opposed to getting proposal papers rejected and then like turning to seek help at the last minute. It's less efficient. I think it's better to include that collaboration from the start and early on, so that both sides can flourish, through that. And then just like in general, right? Like I think it's just important to like find your people, the people that value your expertise and your time, and respect your expertise and your time. And then all of these things will fall together kind of organically. Yeah. So that's my 2 cents here on collaborative work across communities. And just want to highlight here the papers that we presented in this talk are in bold. And you can see, it's not just the 2 of us. There's other people, time and expertise that was very valuable here on these studies. And I've also added other papers that we collaborated on in here that we didn't talk about today, but still part of this collaborative research that we've been doing together. Yeah. So that's it for me. Thank you.
Thank you so much to both of you. This was a very interesting presentation. If you are listening in the audience and you have a question, you could either put it in the chat, or there is this Q&A function as well. I'll go ahead and read. There's one question in the Q&A from Madeline Bauer, and she asks, what sort of time window do you consider when looking for a change point? A window of months or years? With respect to the decrease in cooling aerosols, did that decrease happen instantaneously or maybe over several years?
Maybe I'll answer the first part and then you can answer the second, Claudie. So when you're looking for change points, you typically will have a minimum segment size that you want to look at. So theoretically, that is like the minimum theoretically is like how many observations you need to fit the statistical model. But practically speaking, you might want to make it larger than that, because you might want to overcome some like misspecifications. You can often increase it slightly to overcome some misspecification of the model, especially if you've got some outlying observations and things like that. Sometimes they can get be detected as changes, so you might want to make it a little bit larger. In our study, we use the theoretical minimum, so depending on the model that we were fitting, that could be as small as 2 or 3 observations. We were looking at annual observations here, so that'd be 2 or 3 years, versus potentially larger ones for the larger models where you have you've got intercept, trend, the AR parameter, and also the variance that you're estimating as well. So yeah. Claudie, did you want to take the second half?
Yeah, I can just quickly follow up on the aerosols part. So aerosols are short-lived and they can change really fast. And the reason why we are looking at them to explain a recent acceleration is that there's been changes in regulations over shipping fuels. And those changes in regulation took place over like specific years, basically. And I can't remember the exact details here on top of my head, but there were changes in 2010, and then I think another set of changes in 2012, and then another one more recent, like in 2020. So yeah, I think potentially, global scale as well effects. Yeah.
All right. So we have 2 more right now. But Rebecca, it looks like you answered Derek's question in the chat. Let me.
I can answer in person. I've only half
okay.
answered in the chat. So yeah, so Derek asks, do any of the commonly used change point methods account for autocorrelation across the change points? So And then how plausible is it to assume that independence across the segments? So it really depends. So when we're doing that continuity constraint, you're naturally having dependence across the segments because you have to be able to join it. So you have to have some kind of dependence across the segments to be able to do that join. Luckily, collaborators at Lancaster, Paul Fernhead, Idris Eckley, and Rob Maytone came up with a method, CPOP, which allows you to reparameterize that so you are that continuity constraint doesn't translate into dependence across. So they managed to do that to be able to speed up those algorithms. In general, if you've got short-term autocorrelation, which is what we're assuming here, then you only have a very small window around the change point where you do actually have dependence between the observations, and the approximation that you're making by assuming independence is extremely tiny there. So there's also some theoretical work by Marc Lavielle, who also showed that is negligible relative to the variance that you're seeing in the data typically. So that's kind of one approach. And then they also say, how plausible is it to assume independence across the segments? So I think most methods don't take account of that dependence within a segment, let alone across the segments. So there was another question in the chat that I answered as well, which was around, can you include covariates with it as well? So if you're wanting to include covariates, that's something that you can do, but typically you would assume that the relationship with the covariates changes at the change points as well. If you're wanting to assume that to be, global and doesn't change over time, that can be, that breaks that independence assumption, which is challenging. With co-authors, I'm currently working on a method to try to fix that, solve that problem analytically. So watch this space for something coming out there. Typically, you normally would do some kind of iterative approach because the challenge with change points is you can't really check the assumptions beforehand. So because the change points affect your all of your diagnostics and anything else that you want to do. So if you're fitting covariates, you would fit covariates, but if there are change points within the data, that will affect that estimation of the fit there of the covariates. So you kind of have to do, currently you would do more of an iterative approach. You fit the covariates, you try and find change points. If there are change points, you take account of the change points and you refit the covariates to update the update the estimates of those, and then redo the change points to check that they're the same. So yeah, sorry.
Can I just follow up here, Emily? Is that okay?
Absolutely, yeah, please.
I saw a question from Asaf about covariates and specifically El Nino Southern Oscillation, volcanic activity, and solar radiation, right? And I just wanted to follow up on that. And so in our paper, the last paper that was discussed in the presentation, we decided to stay away from including any of those covariates for some of the reasons that Rebecca just mentioned, and just look at the raw temperatures, because depending on how you do that adjustment, you might bring into some bias. And so I think that we just need to think a little bit more about those adjustments. But if you just do like a simple one, right, where you assume a linear relationship, for example, with El Nino Southern Oscillation and correct for that effect, and then look for change points, and kind of repeat the analysis with those with the global mean surface temperature basically adjusted for El Nino Southern Oscillation variations, we kind of get the same result, right? So it doesn't impact the conclusions here. Yeah.
Okay, we have 2 more questions in the Q&A. I think we probably only have time for one more. And so maybe we can answer the second one offline. And this one is a little different than the previous ones. This one's from Naomi, and she asked, do you have any advice for a statistics PhD candidate who is trying to get a postdoc or research position in time series and climate data analysis, but whose research thus far doesn't overlap?
Reach out to me and I'll help you find your people. Yeah, I think my advice is to reach out to people, maybe try and attending some of these conferences that bring the two groups together that I mentioned earlier, right? Like the International Meeting on Statistical Climatology, for example. And then, you know, try to connect with people that way, you know, and then there might be some like overlapping interest. I think that the research in climate science is rapidly changing also. You know, there's more and more climate data science institute and so on, and it requires, right, PhDs coming out of statistics. So I think that there's definitely room and possibilities, right? And
I think I'd
it's
say
important to reach out. Yeah, sorry, go for it.
I think I'd say on this point as well. So I have a PhD student finishing who has done a lot of work in health and wants to get into environment. So I have a student directly in this position, and the advice that I've given them is around, you know, looking at the things that you've done from a statistical perspective. So I use change point models in a variety of settings. Okay, if I wanted to go into a new area with you know, wanting to look at change point problems in a new area, I need to be able to look a little bit in that area and see what sort of data they're working with and how my expertise might actually be able to help that area out. So I would say when you're doing your covering letter, you want to be very, very clear that you have done some you know, some effort on your part in actually looking at maybe the papers of the people that the group that you're applying to, and be able to actually say how your skills currently that you have might be useful to them. And I think that's one of the key things that's going to set you apart. Often a lot of you know, my other collaborators in environment, you know, they say we really want to hire statisticians, but we want people that can actually engage with us and talk with us, and we can understand what they're doing. So being able to convey what you do, statistically speaking, to an environmental scientist, and in a way that they will be able to understand and receive it. So yeah, so I think that's the key thing that you need to do in your covering letter to be able to show that you're going to be of use to them, I would say.
Awesome. Thank you for that. And as I said, I will try to get to the other question in the Q&A afterwards. But I would like to thank again both Claudie and Rebecca for doing this initial seminar, and everyone for attending. I think this was great. I definitely learned some things, especially I've never heard called a covering letter before. So I even got to pick up some UK terminology in this seminar.
Sorry, cover letter. That is a UK terminology. I'm sorry.
Yeah, that was great. I feel like I learned something. So yeah, again, thank you so much for everyone. And yeah, I hope you all have a good day and join us for next month.
Thank you very much for hosting as well, Emily.
Yeah, thank you.
Yes.
Yeah, thank you, Emily, and thank you all for attending.